So this is what we're looking at. We've got our derivatives of our 6 trig functions. These are things that we need to commit within our heart. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. The derivative of cotangent of x is negative cosecant squared x. The derivative of secant of x is the tangent of x times the secant of x. And the derivative of cosecant of x is negative cotangent of x times cosecant of x. And these 4 we just looked at, and we looked at how to solve them using the quotient rule based on what we know about each one of these, their relationship with sine and cosine. Now, let's get on to this rational expression with root. So we've got the square root of the 5th root of x, which we're going to write as y equals x to the 1/5 power. And from that, now we can simply use the power rule. Once we've rewritten this in x to the nth form, what happens here? That becomes 1/5, right? And then what is 1/5 minus 1? Negative 4/5, because it's 1/5 minus 5/5, right? So that'd be negative 4/5. But we're going to write it back in the form of the way it was written. So I'm going to write it as 1/5x to the positive 4/5, which would become 5 onto the 5th root of x to the 4th power. Now, I would accept any one of those as the answer, but on multiple choice, if it starts off like this, chances are pretty good that your answer is going to be written in that particular form. So, now what I want to look at is I want to look at relating, and those, basically everything we've done with shortcuts of derivatives will be on a quiz next time, and it's going to be a 10-question quiz. The next thing we're wanting to look at is what derivatives look like graphically and how we can relate to them. So I'm going to give a problem here, or a graph, just a random graph. And I'm going to graph out something that looks like this. Now, this is my graph of g of x. I want to know what the graph of g prime of x would possibly look like. Okay, well, I want to analyze it a little bit more than that. You're on the right track. Now, think about what's happening to what's in common with everything to the left of the y-axis here? Decreasing, right? So that means if the graph is decreasing, then the derivative is negative. So I would have negative values for my derivatives here. So this may be like negative 10 up here. This might be like negative 6. Somewhere right in here I'd have a slope of negative 1. And then what's my slope right here? 0. So if I'm graphing the slope values as my new y values, then, or I should say g values, then I'm here, 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 until I get here. And now I move to the right of the y-axis. And what am I looking at as far as the right of the y-axis? What's in common with all of those values? We're increasing, we have positive slopes, right? Now these slopes in here are a little bit closer to 0, right? And the further we get away from the y-axis, the steeper the graph's getting. So we have greater positive values there. So we're looking at something that would do like this. So this would be a graph of the derivative here. Now, we had someone point out just a second ago that this derivative would be a line. just from looking at it. Now, think about what this is. What this looks a lot like a parabola, right? And what is the form of a parabola as far as an equation is concerned? X squared. Now, its vertex is on the y-axis, so it's going to be in the form of x squared plus or minus a constant. So let's just say that this would be y equals, or g of x, I've called it g of x. So let's just say that this would be g of x equals x squared minus 1, okay? Well, if I gave you this as an equation, what would its derivative be? 2x, yeah. And doesn't this look like this could be the graph of the line y equals 2x? Say that again. If I take the derivative of this, you're good. Okay. Any question there? All right. See, all this stuff ties together, doesn't it? That's pretty neat. Now, let's go a little further with this. Let's look at another graph, and let's, again, graph what the derivative could look like here. So let's say we have y equals, and, well, never mind, I don't want to do that yet. I want to graph it first. So I'm going to make my graph do something like that. Okay? Now, looking at what I have here, and I'm just going to say this is just for the sake of having marks up here. I'm going to call this 1 and this negative 1 and this 1. That may or may not be where it is, but when I use terms to describe it, it's going to be easier to use terms with numbers here. So what's in common everywhere to the left of negative 1? Decreasing, right? We're decreasing everywhere to the left of negative 1. So what do we know about the derivative values when we're to the left of negative 1? They're going to be negative. Now again, these negative values are going to represent steeper numbers than these right here, right? They're going to kind of come into where this would be maybe like negative 1/2 and then negative 1/4 and then 0 or something like that. So I'm going to go up to, and again I'm going to put negative 1 here, and I'm going to come up and it's going to look something like this, right? All right, now let's skip negative 1 to 1 and let's go to the right of 1. What's happening in this graph to the right of 1? We're still decreasing, right? Which means that the derivative value should be represented by what kind of numbers? Negative. And just like this one, these slopes are pretty close to 0, right? And then we get steeper and steeper with negative values, so we would come less and less right here. So we're here, well, I need to line it up a little better. So this is kind of under there, so we're here, right? Now, what is true about between negative 1 and positive 1? Our graph's increasing, right? Our graph is increasing. So our slopes should be positive. Okay, so we're positive right here, but we're not much greater than 0, right? And likewise right here, we're positive right here, but we're not much greater than 0 here either. And our curve would actually be the steepest right in here. So we would expect to have our highest positive value here. So we come up and we're looking something like that. Now again, this is a cubic equation, probably. This is a cubic equation. and it would have a negative leading coefficient because it starts upper left and ends lower right. So we would have a negative leading coefficient. Well, what kind of parabola is this? It's one that opens downward, right? So we would expect a negative leading coefficient with it as well. Does this make sense?
Yes.
Good, 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 good. So, let's go from here